it can be extremely difficult to try to visualize graphs of function in actually 3 variables or more. It can be extremely tough to do. These graphs of 4 variables are simply thought of as a surface. Typically, we think of it as a surface that's moving through time, with time being that 4th dimension or that 4th variable. Now, because we live in 3 dimensions, obviously it's a little bit difficult to picture something happening in 4 dimensions. So what we do is very commonly, just like kind of like a contour plot sort of a thing, we'll take and make that 4th dimension a constant. Only rather than a contour plot, because I have 3 variables left, I will actually get a 3-dimensional object. So I get 3-dimensional objects for different values of time, if we're thinking of time as being that 4th dimension. So consider this function f of x equals x squared plus y squared plus z squared. Well, you know right away that for specific values, say k, that this is a sphere. So what we would logically think is happening is for different values of k, I'm going to have a sphere of different sizes. So let's take a look real quickly at Maple and see what Maple can do for us. So here I have an implicit plot, and I have this function for 1, 2, 3 different values of k. So if I plot this now, what I'm going to end up with is, well, like I said, this sphere. But notice the way I did this, if I turn this around a little bit so you can see into it, what I actually have going here is this is one sphere that with the smaller radius, which is for the radius of 4. Then the next layer is like the radius of 9. I'm sorry, radius of 2, square root of 4. Radius of 3, square root of 9. And this last one is for a radius of 4, because it's the square root of 16. So this helps us visualize what this surface must be looking like. And if you think of this 4th dimension as time, what's happening is we have a sphere that's getting bigger and smaller. And obviously, when we think in terms of our range is going to be from 0 to infinity. So if we need to need to visualize a function, like say in 5 or 6 variables, the only way we can do it is by saying, all right, what do these variables actually mean, and what happens if I select some of those variables and make them constants. The bottom line is in order to actually graph this, I need to get it down to 3 variables so I can plot something in 3 space, meaning every other variable is going to have to be a constant. Now, one last thing that I want to talk about here in this section is the idea of functions in many variables. If I have a function in many variables, x1 through xn, and it has the form c1 times x1 plus c2 times x2 out to cn plus xn, we can often use a much more compact notation that uses dot products of 2 vectors. So if I let the vector c equal c1 through cn and x equal x1 through xn, then I can say that f of x, and now x is a vector, is actually equal to c dot x. This is a very nice compact way to represent multi-dimensional functions. So I don't have to write like f of x, y, z, t, p, q, r, s, yada, yada, yada. I can just set this up as a vector and make that my x vector, and then all the coefficients would be my c vector inside the function. So I could write this function as a function of a vector. It's really kind of nice compact notation that comes in really handy at times.